1 hour.
Alright, so for the planning question, right, you know that it's going to be in your practical exam. So you're going to do 1 hour of one practical paper. Then you're going to swap over with the person beside you, do 1 more hour of short experiments, or vice versa. And then you're going to have to put aside all apparatus and finish this piece of work in half an hour without assistance. It is not necessary that it will be related to the experiments you are doing at all. It could be something out of the totally unrelated. Okay, but it's half an hour. So just like your GP essays, you don't write your GP essay the moment you read the questions, right? What do you all do when you all write your GP essays? Yeah, you all have a plan of a skeleton, right? The skeleton for a planning question can be pre-prepared, which means to say, after today's tutorial, you should have the skeleton out. All planning questions should follow my skeleton. Okay, so there are a couple of aspects that I want to talk about today. So you have a 12-mark question, right? But the breakdown of mark for each individual question is actually not known to you, not known to the teachers as well. So Cambridge decides how they want to allocate the 12 marks in a marking scheme. So the examiners will get a marking scheme. We won't know what's in the marking scheme, but you can be sure that if the question is quirky in some way, the mark will be allocated to those quirks. Okay, I'll tell you what I mean. So, for example, these are 5 aspects of your planning question that you should address in sequence. Okay, your planning question, you should write all your answer in point form. You should use headers. So make it look like notes rather than an essay. So I look around and some of you are like writing essays, some of you are writing point form. So that's the beauty of physics. No need to write many essays, right? So everything in point form, that means you can use gigantic headers like diagram. Then you draw your diagram. Procedure, then you procedure 1, 2, 3, 4, 5. Then analysis 1, 2, 3. COV, COV1, COV2, and things like that. So you can make it very notes-wise. So it's very easy for the examiner to understand what you're doing, very easy to read, and also very, very easy for you to write and remember what you want to write, because you don't have to write in an essay format. Right? The mark allocation will depend on the individual case of the planning question. So later on I'll go through question 2. So those of you who tried, good job. So after going through this, I'll give you all some time to see whether you think you missed out anything from my lesson. Okay, then we'll go through the mark scheme together and see whether how many marks you would have scored and how many marks you will now score after making the modifications, okay? Those of you who didn't do, you're going to work a little bit faster. When I go let them have time to modify, you all can just try question 2 on the spot. Okay, so we're going to use question 2 as an example. Okay, I'll go through some idiosyncrasies of each of these in detail, and then I'll give you all the time to do it, okay? Okay, so for your diagram, right, don't just draw a random diagram. You see the question, usually there's some kind of setup that you need to move or change things. Your diagram should reflect that. I'm not saying like, oh, you know, you do a stopwatch experiment, so you should draw in the stopwatch. That's not what I mean. But what I mean is like, okay, you know, in question number 2, you're talking about distance moved from a light source. So you might want to draw a diagram that shows that you can move a certain distance away so that you can indicate where D is on the diagram. Right, so basically what I mean is you should try to label as many useful things as possible. For example, if it's a voltage supply, you label the voltage of the voltage supply. If it's DC, you tell me it's DC voltage 12 volts. Or if it's a variable voltage supply, you can say variable voltage supply, so that later on you can talk about what you want to set it to be. Sometimes it's smart to create problems here that you can solve here. Right? Especially under COV, which is harder for you to think of. Yep. Do you have to say something?
I was saying that the source from it is 3D.
I mean, okay, so a second thing is try to avoid drawing any 3D pictures. Try to draw two-dimensional pictures where it's easy to draw. Basically, don't give yourself a lot of problems. Right? Try to draw like side view. If you need to draw two views, then you can draw side view and top view. If it's a circuit, you need to label your circuit components and use the correct symbols for them. So the diagram mark is quite easy to get to 1 to 2 marks, okay? But usually there's some specific thing they'll look out for, and if you didn't show it, you won't get the mark. Okay? Later when we do question 2, I'll show you what I mean by that. So in the procedure, right, what we'll have is a preamble. Preamble basically means something a little bit more than just set up the apparatus according to the diagram. You should have that at the start, but include 1 or 2 lines more on some specific idiosyncrasies of the question. Like for example, if everything is supposed to align in one line, right, that's when you'll want to say, making sure everything is aligned. Right, or making sure this is perpendicular to the ground. You can repeat it again for precautions, that's fine. Okay, that's the preamble. There may or may not be a mark for that. Okay, I'll later tell you how to look out. But the second thing is very important. Instructions on how to get one set. So you all did your practical experiment before, right? They will tell you how to get one set. Then they'll tell you to repeat for 6 sets in total, then plot graph. You are creating the instructions, but you need to be more detailed than the practical worksheet. Because apparently idiots are doing your practical exam. So you need to make the question paper more idiot proof, right? So there's 3 things to look out for. Number 1, you need to write the instrument. Number 2, you need to tell me the quantity that is being measured.
Do you need to give them units?
No need. Because meter rule already implies the units, right? It's in meters or cm. Right? And last, this is good. It's not necessary, not 100% necessary, but always do this anyway. You know why? Later on when you refer to the quantities again, you can use your symbolic form already because you already defined it once in the procedure. So later when you say, oh, D, they know that D refers to length that was referred to in the diagram. Because you indicated it on the diagram, you tell me what quantity D represents, and then now you define the symbol. You can use the symbol later on in the analysis, and you won't have to redefine it again, and you don't have to spell out length again. Right, so these are 3 things that I would like you all to look out for. Yep, Harry?
If we need to say connect ammeter in series, do we need to say it or we can just read it?
I mean, if it's obvious on the diagram, then obviously you don't need to state it again because it's just setting up according to the diagram. If the ammeter is already in series, it's obvious. Right, but if it's something that's not obvious, that should be in your preamble.
If you want to keep, for example, the distance constant.
The what constant?
Distance.
Distance constant.
Do we need to give a quantity?
No need, but you can say some, for example here, making sure that something is constant. And making sure that something is constant actually is in COV. Later we'll talk about it. Can you remind me?
My diagram is a combination of 2D and 3D. Can I draw a circle and pull it out to show
Yeah, then try to avoid 3D lah because it's hard to draw. It takes time to draw, okay?
I put it out here, that's also here.
Yeah, then just draw a side view can already, right?
Oh, so I can just circle it and...
There's no need to draw a circle, just like side view, right? Yeah. Okay. I'm not done that man, so I need to write some. Okay, I'll write on this side. So, some more. This is after one set, right? Then I need to give instructions on repeating. So the biggest error that you'll write in this is vary D. Okay, you don't say vary a variable. Obviously, we know that the instruction is to vary the variable, but you need to give a little bit more detail than that. So, for example, right, by adding slotted mass of increments 10 grams, obtain 5 So don't just say repeat the experiment 5 more times, or don't say vary D 5 more times and measure R as a result. Okay, what you want to say is, tell me physically how to do the varying. For example, if it's by adding slotted mass, say add slotted mass. If it's by cutting away pieces of piece of your pendulum in the T-shaped pendulum experiment, then just say that. Okay, then obtain further sets. Okay, so by now you should realize that some of the working that you all wrote is a bit incomplete, right? Okay. One more thing.
If some extra, we can't even.
So, for example, now, right, it's a good time, like, oh, after taking this set of readings, okay, and you're supposed to go and calculate another variable that you want to plot. Say in the experiment 2, you're supposed to plot resistance. But resistance comes from two measured quantities, V and I, right? So here is when you will say, after this, you will say, calculate R equals to V over I. Okay, but then to know this, actually what you had to do is to do the analysis first before you know what you wanted to plot. So that's why I said doing planning before you write your planning is important. Like an essay, you need to have an outline and a plan of what to write first. Otherwise, you're going to write, later you finish this whole section, you realize, hey, yeah, I never tell the person how to get R, but then I want to plot R already. Then you need to go and, modify this. Then that's the time that you may forget to put things like, ammeter, voltmeter, all that. Okay, so basically it's do your planning first. That's why I say here, check the analysis portion. Because the next thing you want to do is analysis. So C is analysis, basically the work that you would have done after plotting your graph in the exam question for the normal experiment. Here you are giving instructions on what to do, which means including calculations as well. So before you even tell them what to do in the analysis section, you should write analysis, then you show your working on how you linearize the equation, right? So that it's obvious of what to plot. So that they know, oh, the reason why you want to plot A against B is because it came from the equation and then like that. Then you make the command statement, plot a graph of y against x. So the y and the x should already be indicated from the calculation in the procedure. So one of the steps of the procedure would have to have it already. So for question 2, for example, you already would have instruction on how to calculate r. So here, no need to say calculate ln r earlier because r and ln r is not a very big change. But then r is 2 variables, v over I, then the one you want to ask them to calculate beforehand. So here, for example, question 2, you say plot a graph of ln r against ln v or something like that, right? So this is what you instruct them to do. And then give further instructions on exactly how to calculate the constants that are asked for. So instead of saying that, oh, you can obtain A from the graph and B from the graph, don't give it a vague answer. Give it a specific statement and say A equals to gradient of the graph and B equals to the y-intercept of the graph, or e to the power of y-intercept of the graph or something like that. Now this is easy because you've already showed them your linearization work. Right? If you show them your linearization work, then doing this will be easy, very obvious. Right? And you also won't make mistakes here if you did this sequentially. So just some things to look out for.
You need to ask them to record and measure and record the constant variable. Let's say I'm here. Let's say the current.
Is it needed?
Yes.
To do what?
But it's constant. To calculate R.
To calculate this value? Then it will have to be one of the instructions. So let's say one of the lengths are required to compute the value of b. So for example, the y-intercept may be b plus some length, and then the length is something that you can't fix in the experiment, right? Then here you will just say measure and record L, the length of the wire, using a meter rule. Then later on you can refer to it B equals to y-intercept minus L. Okay, so that's why I said, here you will use the instrument quantity and symbolic form to preserve all of this. Okay, let's discuss D and E. So for D, right, have two COVs, and for E, we will have 1 to 2 safety, and try to give me 3 accuracy points. Okay, so the difference between accuracy and control of variables. In control of variables, right, we are looking for the experimental variables that are going to be kept constant, which means we need to explain this as how do I keep something constant. Okay, for example, in my pendulum experiment, right, I can change the length of the pendulum and I can change the weight of the pendulum bob. Okay, we know theoretically the weight of the pendulum bob doesn't affect the period, but let's say it does. So one of the control
variables would be,
if I were to change the length, I need to say something like, ensure that the mass of each pendulum is kept the same by making sure the number of slotted mass is 3 slotted mass on the experiment at all times. Something like that. Okay, so look for the variables and mention how to keep it constant. So don't just tell me what the variables are. That's the biggest mistake. Don't say that, the mass is the control variable. You must say how to keep it constant. Okay, I'll give you another example. So question 3 talks about pressure of a gas. So let's say I want to keep the pressure of a gas constant. Okay, that's not the question 3 answer. Okay, question 3, you will need to change the pressure. But let's say I want to change the pressure of a gas. I want to make the pressure of a gas constant. You can always say something like, connect a pressure gauge to the chamber, and before the start of each experiment, ensure that the pressure gauge reaches the same value. If it is higher, release some of the gas first so that it falls back to the same value. So basically, control variables is don't give me a 3-word answer and tell me the variable to be kept constant. Tell me how to keep it constant by experimentally. Because planning question is an experimental question. You're supposed to give experimental answers. Right? How to practically do something. Okay, accuracy, right, seems similar to control of variables, and sometimes they are similar, but they are phrased differently. Control variable is how do I keep something constant? Accuracy is how do I reduce the effect of a random error. So in question 2, we're supposed to go and measure light falling onto a light-dependent resistor, right? I mean, that's part of the experiment. But you can have ambient light. So which one should I classify it in? Control of variables or accuracy? Well, if you think about it, actually I will put it as accuracy because the ambient light can change over time. Right, so I want to reduce this effect. I will just say I'll put it in the dark room. But if you phrase it correctly, you could also write it as control of variables. Okay, so if it's a random error, it is better to address it under accuracy. Then don't just tell me that's the source of error. You tell me, in order to reduce the effect of ambient changing light conditions, perform the experiment in a darkened room. Right? And for safety, that's the last point. For safety, don't write bullshit. Okay, let me give you an example of bullshit.
Short circuit.
Okay, for example, if I do an electric circuit, okay, don't say avoid short circuiting the experiment with water when you're drinking from a water bottle, because water is not used in the experiment. However, if you're doing the thermistor experiment, remember our thermistor experiment, there was actually water in the experiment. So in that case, it is pertinent not to perform short circuits by spilling the water onto your circuit components, right? So that's one example. Another example is making a trivial situation seem serious. For example, if you're using a 1.5 volt battery, you can't get electrocuted by it. So you cannot say something like wear rubber gloves or don't avoid touching bare circuit components, because that's not going to electrocute you. However, if you're using mains voltage, then that would be one of the valid concerns, right? Because 240 volts can electrocute you.
60 can already.
So basically, my point here is weigh the safety considerations, and it must be something pertinent. Another example, torchlight. You won't need to say wear protective eyewear against a torchlight, because torchlight can't really blind you, and if it touches your light shines into your eye, you can just look away quickly, no blasting effect. But lasers, strong gas lasers, high wattage lasers, wearing protective goggles is important. High intensity light sources, wearing goggles is important. Okay. Another example, LEDs generally don't get hot. So you don't say don't touch the LED, because LEDs don't generally get hot. But incandescent bulbs do get hot. So if you interpret the question in a way that is easy for you, like for example in question 2, you say, in high intensity light source, nobody said it's LED, right? So actually it might be a normal bulb, right? Then that one will get hot. You could write safety and say that, oh,
incandescent won't burn you.
but the bulb itself will get hot if you touch it.
Many incandescent bulbs will fine.
Okay, but the very high intensity light source ones are very, very, very hot. So like, let's say you grab it, right, you will surely get burned. You try to grab it to turn it off or move it, you will get burned, especially if you are bearing weight. Right? So that's an example where the safety will become an issue. So basically, don't rack your brain too hard to do the safety, but don't write too trivial things as well. Okay, so now that we have an idea of how all of this works, let me give you all 10 minutes. Go look at what you have done already for question 2, because I'll go through question 2. If you have not done question 2, you can attempt to see how many marks you're going to get. Those who did question 2, you can use a different color pen to go and try to do some corrections, and then now you see whether you have learned anything new or not. Yep.
Do we need to specify the various values of the variable? Like, we change the variable by whatever to obtain like 10 cm, 20 cm.
Okay, so that one is Then is saying, do we need to specify the values we use? It actually really depends on the question. If you think that it is very, very, very pertinent information, like the experiment won't work, right? Unless I choose those values, then maybe you do. Like for example, in question 2, you're going to say milliammeter. Because you're going to have something that has a lot of resistance, right? So the current is probably not going to be in amps. It's probably going to be in milliamps. So you want to specify a multimeter set to milliammeter mode, for example. But I wouldn't need to go to the requirement of saying that, oh, I need to increase intervals of 1 meter. Okay, in fact, you don't want it to be in meters because then you can't use meter rule, right? You want it to be less than a meter. So that could be in your preamble.
That means like, well, let's say I attempt further sets of data. I don't need to say what I want my variable
set to be, like you can just say by moving the lamp further away, okay, increase the distance to the LDR and then obtain further sets of V and I and R. Okay, so you don't always need to specify, but sometimes if you feel that it's very important, then you can go ahead and specify. Any questions? Yeah. So like don't say increase the value of M or don't say vary M. You
What's the word there? The sorted mass.
by sorted mass of increments of 10 grams or something like that. Yeah. So that's a good way to tell people how to increase the mass. Right? You just say add slotted masses by increments of 10 grams. So sometimes it's hard for you to specify, then don't specify lah. But please give as much detail as possible. Don't just say vary the mass because it's not like there's a knob there and you turn and then the mass changes. Most experiments don't work that way. Okay, so if you did it already, go try to use a different color pen to make some corrections. Did you manage to add anything? Let's see by varying the distance, right? No, by moving the lamp further away. Or moving the LDR further away. Something like that. It's more specific. The distance, correct, by moving so you add one more line by moving the lamp further away, vary the distance between the LDR. So in this case, don't say vary, just say increase, because it's specific to moving the lamp further away. Yeah, Harry?
Can I intentionally create a danger so I can say the precaution?
Yes, but then it cannot be too far-fetched, right? I mean, it's within the confines of the experiment.
As I use a DC power supply of 110 voltage.
Yeah, sure. Okay, then
so
let
the
me.
precaution can be.
Be careful not to touch the exposed ends of the wire. Yeah, I suppose so, because high voltage is being used, right? Yeah. So the temperature examiner will give you benefit of the doubt when there's really some significant danger that you have created. So technically, even if you didn't need to use a 110 volt, if you said you use it, then later on you justify that since the voltage is high. Yeah. Actually 110 volt, is it high?
Yes.
I think it's okay.
It's okay.
Yeah, I know thousands of volts is high danger voltage. But the body resistance is actually quite high. So 100 volts I don't think will kill that. You get shocked lah. 100 volts you get. 240 volts you will definitely get shocked. Because I was a kid and put my leg in the maybe the size was stupid.
Our teacher left us alone with our wire. So all the wires stupidly huddled around the thing and put the stupid wire.
It's quite painful it's quite shocking.
It feels like pins and needles.
It feels more than pins and needles. Pins and needles feels localized. This one feels like throughout your body one. It's like, it felt like it was, maybe that's why I'm not as smart as I should be. I shocked a lot of time, lost a lot of childhood brain cells.
Like the kid that was sitting around that campfire with the
Yeah, Terry?
This is why I love using
Yes, so it depends on what. Like if there's a new variable you're going to create by dividing v over I, then yes. But if it's simply like saying ln or inverse or square, then you don't really need, because you can just simply say plot a graph of x squared. Yeah, but if you're creating a new variable that uses more than one variable, then it's better to just add the calculation into your procedure. Okay, so Sherry's question is, do I always need to mention the calculation of the final thing that needs to be plotted? Don't always need to. If it's something simple like doing ln or quadratic or sine something, that's okay. But if you're creating a new variable for more than one variable especially, like resistance, okay, you can see resistance uses two variables to get one variable, right? Then you should put this in your procedure. Like immediately after measuring V and I, that statement, you should say, immediately calculate R, where R equals to V over I. Then later on, here you'll be collecting sets of R and D instead of V, I, and D. Right? Because you already gave instructions on how to get the R. Don't throw this here. It's food.
Yeah. To state all the apparatus for values.
No, so, okay, there's something that you don't need to state lah. Like you won't need to label ammeter. Like you put the circle, right? The A inside. It's obvious it's ammeter, voltmeter, right? But if it's something like a power source, then you might want to indicate 12 volt power source, variable power supply, something like that. Something non-standard.
This case is a multimeter.
But multimeter, you write it as a setting. That means if you're using a multimeter, you still write it. If you're using the multimeter as milliammeter, you write milliammeter. M, small m, capital A. Yeah, you don't write multimeter because multimeter is big, right? You don't know what setting.
That power source that can control both voltage and ampere at the same time.
You can't control current.
Can with some power source.
Oh, that means the power source has variable internal resistance.
If you know the model number, can you right?
Okay, yeah, no, it meant no.
How do you minimize internal
I know the model number and how it works.
internal resistance?
Why we need to minimize the internal resistance?
Yeah, no.
What the heck is experiment?
Oh yeah, it's very high.
You're just measuring the voltage and current of the LDR directly already.
No, but I legitimately know the model number. That's how I did my experiment.
No, man.
It's a but like it makes life a lot easier. You just turn a knob.
No, but let's say I'm performing this experiment, right? And it is not important, right, that I use that particular model, right? It's confusing for me as an experimenter.
Yeah, but it's way easier than having to set up a circuit with resistors.
Okay, let's say you need to keep current constant, yeah, but usually you won't, right?
No, because like isn't electricity experiments voltage power more important than voltage and like for the light.
No, voltage is more important. Most important.
For the light.
For light source,
Power.
your light source has fixed resistance, so you just need voltage. Voltage. So you're talking about light source, right? How to keep the intensity of the light constant? Yeah, you connect a variable power supply to it and ensure that the voltage is applied is constant. So you create a power run to solve. Yeah.
When you draw the diagram for this question, do we need to draw the DC circuit for the lab?
No, but you need to draw a circuit for the light. No need to be
Oh, so
don't need everything. You just need to like have say something like power supply. It will be useful. Right, later I'll tell you why.
Oh.
Anything of power supply. High
They
intensity.
provide you the apparatus already. They say it's a high intensity light source. Okay, I'll tell you why you shouldn't use a torch. Okay, because later you're going to write control variable that the light source intensity is constant.
Because torchlight is less consistent in terms of
Then applying a voltage over a bulb.
you can easily control the voltage of a bulb, but you cannot control the intensity of the bulb.
So we can always use the battery for that.
Or you can just use a UV. You can just use a laser.
Is it for all the external lights or has a separate?
Good, because you can use that as one of your control variables. So it's good to do it. Right? Okay, so I'll show you all lah, not to worry.
The highest is the most the highest energy Oh, now thank you. I don't know
Is it off that one and on again?
or something like that.
When did it black out?
Yes. Some even this one.
This is the advanced version of have you tried turning it off and on again?
It's turning it off and on again with procedure.
This is the only way to do it.
Yeah, I do that for my like Wi-Fi as well. When Wi-Fi goes out, it is must turn off the plug and then turn off the mains for the one in the back. Then after that, just wait 2 minutes, 3 minutes, then sequentially turn everything on.
But it works.
Then it works.
But you ask them, it works. You know, 100% of the now.
Yeah. Okay. Okay, man, I'll take it from here. Go try the question. Is that why you don't make any changes or you are redoing?
Oh, and DC source COV cannot use AC source.
No, AC source is fine. This is an LDR, not a diode. So this will give you maximum number of, something like this will give you max number of marks. Let me project and show you one. So this is a sample marking scheme. Okay, so now you can mark your own work, yeah? Let's take a look and see how many marks you will have gotten. So this is the marking scheme. 2 marks is allocated to the diagram. The first mark is for showing that the LDR has an appropriate circuit and the lamp is independent of the LDR. So in this mark, you don't need that lamp to have a circuit. As long as you can draw the lamp separate in a separate circuit, you'll be okay. Right, so you must show the LDR. Right, LDR symbol is something like this, or with the zigzag inside. Okay? The regular resistor symbol with light shining on it. So of course you can just say LDR here to be more complete. Okay, you can see that I've included my instruments as well. Now, workable arrangement with lamp and LDR aligned and secured. Basically, you go to, if you did your planning ahead, like you plan a skeleton of your answer, you're going to realize that you're going to need to have D increase somehow, right? So either your LDR needs to be moved further away or nearer, or your variable light supply, so your high intensity light supply needs to be moved further or nearer, right? But this will only work if they are aligned horizontally so that you can conveniently do it and measure the distances at the same time. For example, if it is like not fixed, right, then you might end up with different heights. Then the correct D will not be a horizontal D, it will be a diagonal D.
What about insert the vertical?
Yes, then you need some kind of like tripod so that you can raise and lower it. Then you need to draw that out. You can say top view, something workable. So that's why the question says workable arrangement with lamp and LDR. So in my case, I'm going to use tripods so that I can keep the height constant so that I have horizontal arrangement. And I'm going to mention that in my preamble because in my procedure, the first thing I'm going to say is set up the above apparatus, taking care to ensure that the LDR is aligned horizontally to the lamp. Right, so basically I want the horizontal distance to be variable. Right, so I'm just going to state this. So there was no mark for it because it was part of the diagram mark in the end, but I didn't know when I wrote it, right?
Oh, it's not CLV.
You can also write it later on. You can still write it later on.
Mr. Zhu,
Yeah?
why do we need a circuit for the lamp?
Later.
On the
Later, okay. So you see here that I actually have all three things to look out for each measurement. Measure the length D with meter rule. So actually I should write in my preamble that I should set up with D roughly 50 cm. Okay, that is because I want to use meter rule. However, you don't really need to write this if you're using something like measuring tape because measuring tape doesn't have the 1 meter length restriction. Okay? Right. Then record the values of the millimeter, the instrument, for current, symbol. Voltmeter for PD, V. So now I got all three quantities with 3 instruments, 3 quantities and 3 variables for them. Then later on I can refer to those variables. So the next step, calculate the resistance of the LDR, R equals to V over I. So because I already wrote V and I here, I can just use back the symbols without explanation.
Do we have to say mini ammeter?
You should. It might be a marking point, but in this case it wasn't. In this exam it wasn't, but it might be. Like, for example, the current is not large enough to be measured with an ammeter.
But if I set the voltage higher, so the current.
How high?
110, 110.
Yeah.
I mean, it will still be small because it's bag or something.
You see that even if you use a normal ammeter, this will be a bit small for it. You get one SF. So that's why you should still use a milliammeter.
Okay.
Right. So this is where your preparation will actually help. You can do a bit of pre-calculation. make the statement for repetition. You can say, like you can label this step 2, step 3, then you can say repeat step 2 and 3 and obtain additional steps. However you all want to write it, it's okay. As long as you have indicated that you have a mechanism for moving the lamp further or nearer, or the LDR further or nearer by moving the tripod, or say by moving it horizontally, then you can get your 1 mark here. So let's check whether I would have scored 3 marks for the procedure as indicated by the marking scheme. R is measured with an appropriate instrument. For example, using R equals to V over I, where V is measured with voltmeter and I measured with ammeter. So here they didn't care that you wrote milliammeter, they would have given you the mark anyway. Right? So I did that, right, because I did say that R is measured from V over I, and I did tell them how I and V are measured. And I did specify that I is measured with an instrument and V is measured with which instrument. Similarly, the second marking point is for D. D needs to be measured with meter rule, measuring tape, something appropriate for the size. Okay, so you want to avoid something like vernier caliper or micrometer screw gauge, because even though you measure size, it's not appropriate.
It's measuring tape. Okay.
Yes, measuring tape. I said, what did I say? I said tape, right? Yeah, measuring tape. Like, you know the one thing, yeah, that one.
Then you like slip it a little bit so that it's
yeah, correct. So that was a good example, right? Lastly, I said vary D by moving it further or nearer the light source, so I gave a way to vary D, right? And that would have gotten me 3 marks. Okay, analysis. What's my equation? Can someone tell me?
Log R equals K plus
No, basic equation.
R equals K D N.
Okay, D to the power N. Thank you.
Oh, do you still need to write down the original equation? Or you can just give them the manipulator one?
I think you should just solve it for them. So for analysis, I'm going to start with R equals to K D to the power N. I'm going to show them my manipulation, that how I get the equation. I'm going to make a statement to say what to plot. Okay. Then I'm going to say I obtain N by calculating the gradient of where N equals to the gradient of the basic graph, and K is 10 to the power of the y-intercept of the graph. So you can write a statement there. I'm writing short form, but you should write a statement. Calculate K where K equals to something. Okay, so let's check whether I have gotten my 2 marks for analysis. Do I have a description of what graph to plot? Yes, I'm very specific, right? And next, do I have a description of how to find the constants? Yes, I have. So this will have gotten me 2 marks. So this amount working. So I'm going to say COV, but I want to ensure that the intensity of the light source is constant by using a fixed voltage supply. So it shouldn't be intensity of the light source, it should be power of the light source. Right? And then the intensity will of course drop as I move the light source further away, because the intensity is what's received. So there's actually of course multiple methods. You could say like constant current, constant EMF, constant voltage, constant power. Just mention some way to make it constant.
How do you ensure constant current or constant?
Use an ammeter
What?
and then adjust your source until you get it.
Just write the model number.
No. What the type of instrument is acceptable, but not the model number.
The type of instrument is acceptable.
Yeah. Like
Yeah.
a variable power supply.
It is a variable power source.
No, but this is a variable voltage supply. Okay. Nothing wrong with. There are many model companies that produce variable voltage supplies. Right? No problem. Okay. Please don't read the safety and accuracy on the screen because they're not well written. I will tell you what you should write
Do
instead.
not touch the light source.
So these two are fine. Okay, do not look directly at the bright light source. Wear safety goggles because the light source is a bright one. That's fine. Do not touch the light source as it's hot. You should be like, at the end of the experiment, allow the light source to cool down before handling as it will be hot. Yeah. So that can be fine. But please write it a bit better than this. This is quite badly written, I feel. Okay? Now, accuracy, you can say that we'll perform the experiment in a dark room to reduce the effect of ambient light. Okay, so please elaborate a little bit lah. Okay. Another is we need to keep the orientation of the LDR with respect to the light source fixed. So that we can just say something like, ensure that the LDR is perpendicular to the source of light. And how you can do this is you can use a pair of set squares to ensure that it's perpendicular to the floor. Right? You can just say that. Please do not ever write this. Okay, this is expected. Don't say take 6 sets of reading. Okay, this is wrong. Don't write this. Okay. Keep the temperature constant. Yes, because the temperature of a resistor could affect. Actually, I think this is very minor also. Temperature of a resistor affects its resistance. So you want to keep the ambient temperature constant. But it's not like we are in Western countries where it does can get quite hot and cold within the room in Singapore.
But it doesn't matter because the resistance, the change of resistance won't be that significant.
Yes, the change of resistance is more affected by the current moving through the resistor. So it will get to some equilibrium temperature in the first place.
Can you say that the high intensity light heats up the circuit?
Sorry?
Can you say that the high intensity light heats up the circuit?
No, but okay, how your high intensity light source is, it should heat up to some operating temperature and remain there. So that one won't affect your answer because by right it shouldn't keep getting hotter and hotter. It should reach an equilibrium temperature. Your light bulbs all work that way. Otherwise technically their brightness will keep changing. They don't.
So like heating up the circuit connected to the LDR?
Yeah, not really. The heating effect of the current through the circuit is the most important consideration, and that would give some equilibrium value already. So I don't think that the temperature actually affects the experiment much. Okay, this is something that, okay, although I say that you should always try to write accuracy and precautions that's customized to the experiment that you're doing, this is one that you can actually use in many different planning experiments, so a version of it. Okay, so like just now someone said that, how do I know whether I need to tell them that I need to use specific steps or distances or what? Here's a good way to say it. Now, if your light source is very, very far away, right, the resistance of an LDR will increase very significantly. It will be like mega ohms. And the question actually tells you that too. Then even a milliammeter or microammeter will still give you very bad results. Because the value of the current will already get very tiny. So what you can say is, you should take preliminary readings of D such that a measurable range of R is obtained. Then in your experiment, then you carry it out within that range of values. So basically, you're admitting that your measuring instruments have limitations. Like, I can't measure microamps very well. I can't get much smaller than microamps. So therefore, I can't do the experiment if the resistance of the LDR is too high. So therefore, I will ensure that the light is sufficiently close enough. But how do I determine this? I need to do pre-experiments, like test a bit. Right? So this is a statement you could write. Take preliminary readings to obtain suitable ranges of R. It's a great statement. This one you can use in almost any experiment if you really cannot think of a more appropriate thing to write. Right? Because most experiments, you are really limited by the instruments. Like a pressure gauge only can measure this range of pressure. Can't measure too high or too low pressure. Okay, so that's this experiment. So my answer here would have gotten full marks. How many marks did you get? Hmm? You also get full marks?
So what's full mark?
Almost full marks? Wow, Harry.
What is
Great.
full mark?
Expect 12.
Level 10.
Now 10 over 12 is pretty good. So you realize that if you follow this setup, right, you will get quite close to full marks.
Is it always, for the precaution, is it always 1 safety and 2 accuracy?
No, please write about 2 safety and 3 accuracy for because you don't know how they are allocating much. Just write a bit more lah, huh? Maybe cancel here. So the notes that Mr. Chan gave you all is actually very, very, very comprehensive. There's a lot of apparatus that you all can learn about inside. But I want to look at the question itself, okay? Look at the question itself. Wait, should I give me a minute? Okay. You see here, after telling you about the experiment, you notice that they tell you how to write the answer. A, B, C, D, E, right? Actually, is what we have here, right? The equipment you use, right, would have been indicated in your diagram. The procedure to be followed is the procedure. How to find the constants is basically analysis. So if you write this whole step, no matter what they ask you for analysis, you usually get it correct. Right? Control of variables. Precautions that should be taken is precautions. So what you should do is always follow my template, the sequence I've indicated here from A to E. But look here to see if there's anything else that they want that would not already be included in our template. Okay, I hate to use that word, but yes, I have a template. This is the template. Okay, then you insert it somewhere pertinent. So for example, right, like in this question, it could have been explain how, in your answer, explain how, or carefully explain how to obtain the resistance of the LDR. Then in that case, you're going to need to do some preliminary calculations like, oh shit, they want me to be very careful about the LDR's resistance. I need to check that my ammeter is the correct range and that I can measure it and I've used the correct voltage source. Then in that case, you will want to modify the setup, right, to indicate that it's milli or micro ammeter. And then in the procedure, you will say that calculate the resistance of the LDR using R equals to V over I. And then the setting, maybe you'll say using the micro ammeter setting of multimeter. So just be a bit more careful. What?
Is there a nano ammeter?
Not in your apparatus list, but if you really have to measure nano ammeter, then just say that is a nano ammeter law. Just say it. A very sensitive nano ammeter, whatever. You can, if you're really desperate. So my moral of the story is, sometimes here may have one more thing that they ask you for. Find a part to write it into. Usually you belong into procedure or a combination of procedure and diagram. Okay? Alrighty, have I used up the time yet? Still got some time, right?
We still have 40 minutes.
20. Okay, so why don't you all spend the remaining time to go and try 3 and 4, now that you know a little bit how to write the procedure. The template, yeah. Right? So does this clarify something or is this like waste of time? Did I repeat what you said in the lecture?
No, I don't think so. You didn't mention anything about that.
You just tell us about the apparatus.
Okay, so he basically gave you an idea of what the different apparatus have, but he didn't mention to do this, right? Yes, please do this. Okay? So it's very easy to get like 9 to 10 out of 12, right, in the exam when you follow this sequence, even if you don't really know what the apparatus is. Okay, one very important thing is, please do not say data logger as an instrument. Data logger is not an instrument. Data logger is a computer. The computer doesn't measure things. The computer is a way of record, accepting data and presenting data in a graph or format. Right? So, for example, a motion sensor can measure distances to objects. Then you can say motion sensor connected to data logger. Because the data logger only logs data it receives. So if you want a voltage meter, that can also connect to a data logger. Then you can plot voltage over time. So you're going to be very aware of how the instruments work. You cannot smoke by waving your hand and saying some rubbish. Okay, but there are things like intensity meters. That's how you measure intensity. Okay, there are such things as intensity meters. So it'd be a good idea to know what kind of meters there are for different things. Do you remember how to measure frequency?
Yes.
Of a rotating object? That is rotating faster than your eyes can count?
Use camera, use that camera.
A laser and a laser sensor.
No, a laser can't. The laser itself is light. The light can't measure anything.
Use that camera to change the camera frequency so that you get stationary.
Remember I showed you all that video, the guy used a torchlight that can adjust.
Yeah, the camera that.
That's not a camera, that's a torchlight.
Oh, the torchlight that adjusts the.
Yeah, what's the name of that torchlight?
Forgot.
The torchlight and what?
That can adjust its blinking rate.
So that you could
You
use a
don't
standing
use a
light.
torch. You don't actually need to use a torchlight. You use a frequency. You use a frequency, then you turn the knob. Then the knob will.
Yeah, so what's that device called?
I have the exact model number. You want?
That's called a stroboscope, right? So you need to at least know the name of the apparatus. If not, you can't describe how it works or how to measure. Stroboscope. It comes from the word strobe lights. Strobe lights are lights that flash in a disco. A stroboscope is a light that is able to measure how fast it's flashing. Right?
No, but it's quite useless though.
The stroboscope?
Yeah.
Why? It's super useful.
If your thing is very precise, that is useful. But like if not, right, it's quite useless.
What is very precise?
Like if your LDR is very, it's like.
No, I'm not talking about the LDR experiment. It's talking about, let's say there's a fan blade and I don't know the frequency of rotation of the fan blade.
But stroboscopes usually, at least my stroboscope only went up to like 100.
Yeah, the one in the lab can go to
100
thousands per second, per minute.
No, so they can go low, but they can't go high.
They can go high enough for fan blades.
100 milliseconds is about the max for mine. Mine was 100 milliseconds, the 100 milliseconds.
Okay, maybe the lab one is good. Okay, anyway, go try question 3 and 4.
Usually,